So this is a backpropagation example of a simple function. This function has two variables and is given by f of x comma y is equal to x plus sigma of y, where sigma is the sigmoid function, divided by sigma of x plus y squared. And I think the simplest, this simple kind of function has embedded another function, which is the sigmoid function, let's say, of x, which is given by the expression 1 divided by 1 plus e to the minus x. And this is effectively no coincidence that this is a function that was actually chosen as a sigmoid function. It is sometimes a common activation function in neural networks. And our job here is to calculate the gradient of f with respect to the parameters x and y, and which is actually given with this is a vector with two components, the partial derivative of f with respect to x and the partial derivative of f with respect to y. So this function f of x comma y has just two parameters, and we can actually represent this function with a computational graph. This computational graph, we start right here at the bottom with the inputs of this function x and y, and we can actually gradually build this computational graph by drawing it like this. X and y will actually be summed together. We call each of these operations, these elementary operation, gates, and with inputs and outputs, and we start calling each and every of these outputs a suitable variable name. For example, xpy, that stands for x plus y, for example, in this case. Then we continue. The y will actually go through a sigma function, and at the output we will obtain the sig y variable. The x plus y, as you can see here, will also go through the squaring operation, and at the output of that squaring operation we will have a variable, let's say xpy sqr. The x now will also go through a sigmoid. The sigmoid is the sigma of x that we see here, and it will sum. The output of that will actually call it sig x, and that sig x will be summed with the xpy sqr variable in this gate over here. The sig y plus x, as we see in the numerator, will actually form the numerators via an addition. This addition is going to happen here, x plus sigma y. Okay, so that's the gate right here, and it will actually give us the numerator. We will call it num, and all we need to do is to form the ratio of the two, and we'll form this ratio by taking the inverse of what is effectively the denominator and multiply it with a numerator to form effectively what is our function output f. So I hope this is computational graph is clear, with consisting of some elementary gates, and it's also called data flow diagram, as it actually takes x and y from the input and produces f at the output. And the backpropagation operation now involves two passes. It's a computational technique, so we just presented all the steps. The first pass is the so-called forward pass that goes from the input x and y all the way upstream to compute the value of f. And this is actually called the forward pass. And after the forward pass is completed, we will execute the so-called backward pass. And this is the pass that will actually compute stage by stage, gate by gate, upstream and downstream gradients that we will go through when we reach that point. So let's first execute the easiest path of the two, which is the forward pass. So the forward pass, for it, we will just need to start from something, from somewhere, which is start from the input here. So we will execute first the sigmoid of y. We could execute at this gate, but for now, let's write down first how we obtain the sig y at the output here. It is effectively, obviously, the 1 over 1 plus e to the power of minus y, and that is equation number 1. The second equation that we can actually do very easily now is we can immediately get the numerator, so we can say num at the output of this kind of gate is x plus what we just computed. And this is the second equation. The third equation is we can take the sigmoid of x and preparing for forming the denominator. Sig x is equal, again, very similar to the sig y, 1 plus exp of minus x. That's the third equation. And then we just need to populate this port over here. So we start with the x plus y, xpy is equal to x plus y, and this is number 4. We continue to squaring it, xpy sqr. This is xpy to the power of 2, which is, we can write it down like this, a bit more kind of programmatic way of writing things, like programmatic way of specifying input and output variables. And now we will be able now to form the denominator. The denominator is going to be, and we call it as denom, is going to be equal to x sig x. As you can see here, sig x plus xpy sqr. And this is equation number 6. And now we are actually able to form the, we forgot to add a variable here, which we will call inv denom. And the inverse of the denominator, in other words, is 1 over denom. And this is equation 7. And finally, f is equal to obviously the multiplication of num times inv denom. And this is equation 8, which is really the ending equation for the forward pass. So let's look at the chain rule, which is one of the more, I will call it, foundational elements in calculus, and it's considered to be a background material here for this course. And the chain rule really connects in terms of partial derivatives variables which are associated with a block diagram. Looks like this. We have an input variable x in the m-dimensional space with m components, in other words. It goes through a function g2 or a gate, as we will call it in backpropagation. It produces another vector y in the n-dimensional space, and that vector is via another function g1 is producing a scalar z. And the problem that we have now is how we can actually have some connection between the variability of x and to the variability of z. So this is actually represented with a partial derivative of z with respect to x, and this, according to the chain rule, is actually given by the partial derivative of z with respect to y times the partial derivative of y with respect to x. And effectively, intuitively, this means that that variability from x all the way to z, it's the product of the variability that the x is actually causing to the variable x, and in turn, that the variable x is causing to the variable y, and that in turn is causing to the variable z. And that is really the single-dimensional kind of case, and it can readily be extended to the multi-dimensional case. In other words, when we have m different than n different than 1, and in this case we have derivatives that involve scalars and vectors. In fact, you can start writing exactly the same rule as we have done in the scalar kind of case. And here we have the derivative of z with respect to just one component of x. This is going to be equal to the derivative of z with respect to the intermediate variable y over here, which is a vector, times the derivative of the vector with respect to the scalar x1, which is the first component of x out of the m components total. And you can actually write the derivative of a scalar with respect to a vector as the row vector of the derivative of the scalar with respect to each and every of the components of this vector. So y has n components, so n components are being listed here, times the derivative of the vector y with respect to the scalar x1, to the component of interest in this specific case. So we have again another column vector this time with respect to that lists the associated, if you like, derivatives of all the components of y. Notice that a single component of x will affect all the components of the vector y via the function, via the coupling function g2. And this vector of a row vector times a column vector is nothing else than a product, a dot product, and we can actually write the result, which ends up being effectively a scalar, like this. So I think that it's actually straightforward to understand the direct extension between the all scalar case and the scalar with respect to one of the components of vector x1. And I think when it comes to how come this is a column vector, a row vector, and this ends up being a column vector, I think it will be understood a bit later as when we introduce the general case in a moment. So what is really the general case? The general case is when we have the output z with respect to all components of x, and this will effectively is a row vector of the scalar z with respect to all components of x, x1, x2, all the way to xm. Very similar to what we have seen just a few moments ago. And therefore we can actually readily plug all the results that we get from each of these kind of components, and we can actually write this in a more compact fashion by a matrix, by a vector multiplication. vector by matrix multiplication. So the vector that we have is the carried vector from above as we had it, and here we actually start introducing. Before we only had a single component x1. Now we're going to have x2, x3, x3 all the way to xm components. We're adding more and more columns into this column vector, effectively creating a matrix. And it is this matrix that we will be calling the Jacobian, which is really a fundamental matrix of interest in backpropagation. And it also defines some of the conventions we will follow in terms of dimensionality. And the dimensionality is actually important because it will allow us to check intermediate results, whether or not they are correct and make sense or not. So the Jacobian matrix is always output times input. So it actually refers this Jacobian matrix to this vector function G2 that takes vector inputs, produces vector outputs, and it's always by convention outputs with respect to image. That's one thing to remember, very important. The second thing to remember is that because of that, we can actually write the elements, each element of the Jacobian matrix, I and j, in other words, row I and column j, as a partial derivative of the output I with respect to the input j. That's the second thing you need to remember. And after that, everything will actually flow along. And just to connect what we have just said before with respect to of this derivative with respect, in other words, of a scalar with respect to a vector, we can actually see the Jacobian matrix and see, if you like, the convention, and we can now readily understand why this was a row vector. And in other words, if you look at the Jacobian matrix, this situation of a scalar with respect to a vector corresponds to one of the rows of the Jacobian. So let's take one case where we have a scalar y1 with respect to a vector x1, x2, and so on, xm. This is really the first row here. So that's why this is the derivative. I can write it as, in general, with respect of a scalar, that's a direct convention with respect to it's a direct one consequence with respect to the convention of the Jacobian matrix is going to be a row vector. And if we take the other case where we have a vector with respect to a scalar, where we had, let's say, the derivative of, let's say, of y being a vector with respect to a scalar, let's say x1, this was effectively now a column vector. And you can see it here in the Jacobian matrix. It is the case where we have a vector, let's say y1 all the way to yn, with respect to a scalar. Well, let's take x1, that doesn't change, and it's kind of column, it's a scalar. So this corresponds to a column vector, so that's what we will write here. Just to remember these conventions, which is straightforward after we understand exactly how the Jacobian matrix is structured. So before I start the backwards pass, the backwards pass is certainly an exercise that involves starting from the top, if you like, of this computational graph that we have just seen, and we will be using, I will call it the chain rule, in a bit more data flow oriented sort of representation. So this is effectively one gate G that is receiving from upstream a derivative, in this case be a gradient or could be a scalar derivative. It depends, of course, on what really happened before, and this is the derivative of the target function f with respect to z. That is going to be obviously be calculated itself via a number of stages, but this is actually going to be given to us. This is going to be arriving to our gate, and our job here is to understand how this gradient is flowing through the ports X and Y. Those ports X and Y were effectively the ports that correspond to the variables X and Y in the forward pass. We went ahead and calculated those in our forward pass equations. And those downstream derivatives, as we will call them, those downstream derivatives are going to be written as derivative of f all the way to the top of the diagram with respect to x, and then obviously the derivative of f with respect to y over here. And as it will turn out, this is everything that we need. So we will be using the term upstream gradient. This upstream gradient is actually given, and we will call these guys downstream gradients. That obviously will be upstream gradients for the subsequent gate of as we go from top to bottom in that computational graph. And as it will turn out, these downstream gradients are all we need to calculate them are effectively the upstream gradient that is actually given here, and what we call the local gradient. So let's write down the expressions, because it's going to be really important expressions. So there will be the derivative of f with respect to x is equal to the derivative of f with respect to z, which is what is coming from on top, and the upstream gradient given to us, times what we will be called the local gradient, the derivative of z, in other words, with respect to x. All right, so this is the one equation, and the second equation is going to be the derivative of f with respect to y is equal the derivative of f with respect to z, again, times, the times is actually not strictly speaking correct, but you can think about it like this, derivative of z with respect to y in this case. Okay, so these are the fundamental equations that we will be using for our backpropagation, and these are going to be the local gradients. And they're called local because they only depend on the local knowledge of the gate G. Usually these gates are very elementary, and because of their elementary kind of nature, you will be able, using simple symbolic lookups to understand how the these derivatives can be written, something that will become evident in this exercise as we go now back into that computational diagram. This is the computational diagram that we have, and in this case we need to sort of introduce certain variables. We will start from the top of the diagram, which is actually equation 8 here, and we go all the way to back into the variables x and y. So we'll go into this kind of direction. And let's write down now the first equation. And the first equation we can actually write on the backpropagation side is really all we care about is to calculate this gradient, the derivative of f with respect to x and the derivative of f with respect to y. So we will start from here and we'll write the first equation, which is the derivative of f, and I will be writing these quantities on the sort of left-hand side of the arrows, or whenever we have sort of the empty space in this kind of diagram, as it is a bit congested. So I'm going to be calling this derivatives d for the so-called derivative of f, instead of actually writing derivative of f with respect to f. So we all know the derivative of f with respect to f, this is effectively, and this is equal to 1.0. Okay, this is symbolic derivative of a variable with respect to itself is equal to 1.0. So we have our first, if you like, upstream gradient, and this upstream gradient is now received by this gate, which is our first gate, which is multiplication gate. So let's first, before we forget, write down the first equation. So the derivative df is equal to 1.0. Okay, and so we can say we can actually have now this a multiplication gate, where the multiplication gate is really on equation 8. So the multiplication gate was right here. So just write down again the expression f is equal to numerator times the inverse of the denominator. This was the variable. These are the variables that we have. We are actually looking as inputs in the for propagation to this gate. Now they are the places where we need to estimate the downstream gradients. And in order for us to estimate the downstream gradients, we will need to apply this specific rule and this specific convention in terms of sort of calling what is upstream, what is downstream. So the next equation that we will then go down to downwards to backpropagate is the this gate. So we already have the downstream gradient from this gate, which is the upstream gradient of this gate. So d inv denom is going to be our upstream gradient arriving over here. So let's now write down. So we are going to this equation, equation number 7, in the order presented to us in the forward pass. So equation number 7. So we will basically, backpropagate the equation inv denom is equal to 1 over denom. This was equation number 7, and so we will actually do exactly the same thing as we have done before. We have arrived, we are receiving an upstream gradient, which is the d inv. So this is our gate over here. Now this upstream gradient d inv denom was just being computed a few minutes ago. So this is now the this is I guess just one port. It has just received one port and it produces one port. So we have one downstream gradient, and this downstream gradient we will call it d denom, because that is really the variable that it is coming at the output of this gate according to this computational graph here. Alright, so this is fairly straightforward now. So we will apply this rule. The derivative of f with respect to denom, which we will call it d denom, is equal to the upstream gradient d inv denom times, again the times is not strictly correct, but it doesn't really matter now. Alright, so it is the derivative of f with respect to, sorry, it's not the derivative of f, it is the local derivative. So it is the derivative of inv denom with respect to denom. Okay, so the derivative of inv denom with respect to denom is, what we do is we go, it's a symbolic derivative. Obviously, we are going to a lookup table from derivative lookup table. We know that the derivative of 1 over x is minus 1 over x squared, and therefore we can write this as the d inv denom, which is d inv denom is in fact numerator Again, this is now completely a lookup. We don't calculate anything, we just look up what we already have calculated before, and we apply the one formula over here, which is denom squared. Both of these quantities are known to us because denom was in fact obviously calculated in the forward pass. It is actually present here in equation 6, so it was calculated in the forward pass, and therefore we are able to store it. We have already stored it in memory from the forward pass. We just retrieve it and we immediately are able then to calculate. And this is in fact what we are have just we just backpropagated this specific gate on equation 7. Maybe we have some space to backpropagate now equation 6, which is this guy over here. So let's write down again backpropagation of backprop of the equation. The equation 6 was denom is equal to sig x. So sig x plus xpy sqr. Okay, that was our equation. Which of course this equation corresponds to yet another gate. So what was this actually gate? This gate was this gate is an adder. Okay, so we are receiving the d denom upstream gradient, and now we have two ports. The two ports is has downstream gradients will be d sig x, and the other one will be d xpy sqr. These are the two downstream gradients. Okay, so we apply exactly the same template that we have applied before. So what was actually going to happen is that the derivative of f with respect to sig x that we have called d sig x is equal to the upstream gradient d denom times the local gradient, and the local gradient depends only on the gate, so it is effectively the derivative of denom with respect to sig x. Well, but the derivative of denom with respect to sig x is, so the derivative of x with respect to, the derivative of denom with respect to sig x is effectively 1.0, because this term is actually a 0. So this effectively brings d denom as the answer. And the second derivative, which I will call from the other port over here, the dxpy sqr, it's actually very similar, is going to be ultimately the upstream, which is d denom times 1.0 again, because at that time that we were taking the derivative of this thing with respect to xpy sqr, this is 0 and this is 1.0. So this is going to be again also d denom, which we know from previously. So we can proceed very similarly to backpropagate all the remaining gates over here, something that we have done in the notes. And there's one tricky point in this diagram that we need to pay attention in this kind of backwards pass, and it is actually these 2 points over here. And in these 2 points, these are called forks, or effectively we are actually copy gates. They should be treated as gates. So in this fashion, you have an upstream gradient, and you have another upstream gradient coming in, and there is only one downstream gradient, which is basically the summation of the 2 upstream gradients. So make sure that you have followed the equation in the notes. This equation is involving the backpropagation of sigma x over here gate, and the backpropagation of the gate that we have here on the summer, this gradient over here. So these 2 upstream gradients have to be calculated first before we are able, obviously, to backpropagate through this gate. So finally, after we actually go through these 2 points over here, these 2 actually gates, we will be arriving at the desired result, which is the derivative of f with respect to x, and also the derivative of f with respect to y, which is exactly what we wanted. And this is an example that shows that you can have any function even outside of the neural networking space, and the backpropagation is a general procedure that can be applied to any function whatsoever, even those functions who have nothing to do with neural networks. So in the next video, we will be dealing with some elementary neural networks. Just to reinforce the point, now switch now to the neural networking space and start applying backpropagation with vectors, as those quantities are a bit more common in the neural network space. Okay, thank you.